A wonderful good afternoon, ladies and jelly beans. It's a great pleasure to be with you this afternoon for our little refresher session. And I just wanted quickly a check. Can you all see me? If you can see me, can you please send me a thumbs up, a like? Any likes? Can you hear me? So can you see me? Can you hear me? Send me a like, please. No likes? Let's see. Can you all hear me? Let's see. Tom says, yep. Just click on the like button if it works, please. I'm not after likes, but it would be good to see if these things work. So how many viewers do we have? We have only 2 viewers, actually. I'm not entirely sure if that's if that works. Oh well. Okay, let's proceed and see what happens. So what I want to do in this live stream is I want to give you a little bit of a review of the things that we have done in the BI308 module. And hopefully this is of some relevance for people who are doing lab-based projects or also data analysis projects. So what I've done here is I've stolen some data actually from somebody who said they find it difficult to look at the data and interpret the data. So what we've got here is basically, I think it was probably from an ELISA readout. So an enzyme-linked immunoabsorbance assay or something like that. I can't remember that. And whatever this assay is actually measuring, we have here cells that are untreated. Here we have cells that were treated with drug A, with drug B, with drug C. And what we've done is basically we have taken here 4 samples for, if you like, replicates. And now the question is, really, what does this experiment actually tell us? And how would be the best way to show it, for example, in a scientific journal? So I'm just wondering what's going on here. Is this in any way doing something? Aha. Ah, yeah. So you can hopefully see things. Just a quick check again from the people who are in it. Is there an echo in the audio? Or can you hear me properly? Tell me, please. Otherwise, I have to get my iPad out and see how this works. And just bear with me for a moment. Groups, we are here in this one here. Okay, good. That looks reasonable. Audio is fine. Excellent. Thank you very much, Tom. That's extremely useful. So we've got four samples here. And so let's have a look. First of all, what we want to do, obviously, is we want to calculate the average of these readings here. And the easiest way to do that in Excel is with one of the built-in Excel functions. So what we do is we basically say we calculate the average, and in statistics this is abbreviated with this X bar. And in Excel what we need to do is we put in equals average, and sometimes it does that already for you, so you don't have to do anything. So average, click on it, and then you just simply drag with the left mouse button, you drag it down until you've got all the cells highlighted. So in this case we have cells G5 to G8 here, and all we need to do is, in order to get the average, press enter. So we get the average of these four data is 0.2305. And I can do that now for all the other cells, or I just simply drag the cursor. I wait until it is this little black cross here in the corner. I keep the left mouse button pressed and I just simply drag it all the way. So here I see my averages of the readouts. So 0.2305 for the cells that have been untreated. With drug it's 0.19775, and so on and so forth. With drug C, interestingly, it is 0.25125. So that is our mean, and very often we want to report this mean somehow in a graph. But we also want to indicate what is actually the spread of the data. And for the spread of the data, we would usually use something like the standard deviation. And we need to be aware what we are looking at here. So for example, if we look at our untreated cells, our control, we are looking at 4 different data points. But of course, we could have done another data point here, 0.23, for example. Or somebody else might have used a different experiment. Just remove this. Somebody else might have a different experiment where they got, let's say, 0.25, 0.21, and so on and so forth. So what we are looking here is really sample. So we are looking at a sample standard deviation. We are not looking at the population because the population would be 1,000 of these data points. What do I say? 1,000, a million, a gazillion, infinitely many of these data points. But life is too short for that. So we just deal with sample standard deviation. And the equation for a simple standard sample standard deviation, and we abbreviate that as S, equals. Okay, we calculate for each data point, and I write it as xi, we calculate how far it is away from the mean that we just calculated. We then square this and we sum it all up. And then, because it is the standard deviation of a sample, we divide it by n minus 1. And this n here, that is the number of data points. So these are these 4 data points here. And if we want to have the standard deviation, we just simply take the square root of this. Now that looks really complicated, but what we can do is just, just for fun, we can do the first point. We can say, okay, the first point would be 0.241 minus 0.2305 squared plus, well, the next one would be 0.229 minus 0.2305 squared plus, and so on and so forth. We add this together, we divide it then by n minus 1, so that would be 3, and we take the square root of that. Or we just simply let Excel do that. So here we have a new line, that's our standard deviation. And in Excel, it's very easy. Again, we do equals, and then Excel has the standard deviation function. And as you can see, it comes up here. And if you have an S after the dot, this will calculate your sample. So you just simply click on that. You keep your left mouse button pressed, go down. Again, we have the cells from G5 to G8. And press enter. Now this is our standard deviation. That is 0.0822. And we can again do that for this data set here, or we just simply drag it round and we get our standard deviations calculated for the different treatments. Okay, does that make sense? If it makes sense, please send me a like. Send me a thumbs up, please. Does it make sense? Go on. Okay, so, oh, my beautiful writing disappeared. Need to get this back. Oh dear, my mouse is doing weird things. So that was our X bar, and that was our standard deviation. Now, one of the things that we obviously want to do is we want to say, right, how sure are we actually, so let me quickly write this down, how sure, how confident are we that the average, that x bar represents the true mean of the samples. So how sure, in other words, how sure are we that this 0.2305 is actually the correct value that we are looking at? And we can't be sure, we can only say we are probably fairly sure that our true mean is within a certain range. So within a certain range. That's all we can say, because that is statistics, if you like. So where would this range be located? Well, this range, we could say, okay, we are fairly sure that our true mean is somewhere between 0 and, let's say, 100. Does that make sense to you? Would it be good, or in other words, would it be good if we were sure that the true mean is between 0 and 100? What do you think? On your keyboard? Does that make any sense? Does that help us if we say it's between 0 and 100? On your keyboards, please. Does that make sense? Yes or no? So, well, of course, 0 to 100 is an enormous range, and we don't get anything from that. How about, let's say we say between 0.1 and 0.3? Would that make more sense? Would that help us really? Anyone? Come on, guys. Help me out here. Help me out. Write comments. Oops, I lost my writing. So 0.1 and 0.3, that's probably a little bit better, but we want probably a little bit even better than that. So what we can do is we can calculate what is called a margin of error. Margin of error. And this error, or this margin of error, allows us to make even a better statement about in which boundaries our number here is. So how are we going to do that? So I write this here, margin of error. And again, Excel has a function for that. And here this function, another thing that we need to say is, how convinced do we want to be? And very often we say, we want a confidence level, and very often this is just chosen as 95%. Or we also say sometimes we want a significance level. And that is usually abbreviated with alpha, and that is given as 1 minus the confidence level. So if we have a 95% confidence level, what would be alpha? On your keyboards, come on, give me something here. What is alpha? If we have a confidence level of 95%. What is alpha? Nobody? So we've got four samples here. What is alpha? Anyone? Come on, don't let me hanging here. Hey guys, is it working actually? I'm slightly worried now. I can't see any comments. Hey guys, is it working? Is it working? I'm slightly worried. Or is it just afternoon? Well, I just carry on. It's a little bit disheartening, I have to say. Okay, thanks, Tom. So what is alpha in this case? Obviously 1 minus 95%, so that would be 0.05. Okay, so that is our confidence level. So what we can do now is, so in Excel we can calculate this margin of error, and this is done by equals, and we say confidence point T. Go for the confidence point T, not for anything else that you see here. This confidence T will give you actually the margin of error. So let's click that, and it asks for a few things here. It asks for our alpha in the first place, so that is 0.05. Then it asks for the standard deviation, and the standard deviation we just calculated. That's this one. And then it asks for the sample size. And we had 4 samples here. So 4 samples. So our margin of error is 0.013. And again, we can do that for the other treatments as well. So that is our margin of error. So what can we do with that now? We can actually say that we can say now what we see here is, okay, our mean, so the true mean is our x bar, our mean, plus minus the margin of error. So in this case, in the first case of the untreated sample, it would be 0.2305 plus minus 0.013. So our true mean most likely lies between plus minus 0.013 of 0.23. Does that make sense? I better not ask if that makes sense, but so let's just simply assume it makes sense. Okay, so what can we do with that now? We can, obviously, we want to represent the data in a nice format. So how are we going to do that? Well, what we want is really a nice chart. So we have here the average, and we have here our margin of error. Let me put it like that. So what I do is I just simply copy the data here. So I've got here my untreated cells, average, standard deviation, and margin of error. And now I want to have that as a nice graph. So what do? I go to Insert, Chart, and I want this as a XY scatter graph. Obviously, I forgot to highlight the data. So what I want is basically something like that. I want untreated samples and the average plotted. Okay, now Insert, Chart, XY scatter graph. And what I get here now is nice data points. So this one here, obviously, as you can see, is for the untreated cells, cells treated with A, B, and C. So these are my means. Let's get rid of the x-axis because that doesn't do anything. The chart title doesn't do anything. And I can now obviously also include what these data actually are. So I just put in a text box. So for example, this is here untreated. This is here with drug A. No, come on. Well, drug B, where am I? Insert, text box, A, and this is going to be B, and so on and so forth. And that is C. So, but now it would be really nice if I could do some error bars and if I could actually put these margin of error as an error bar and actually Excel allows you to do that. So how do you do that? You just click, left click on these data points, and you come up with chart design. And I just remove this, and you go to chart design. You go to error bar, like here. You go to more error bar options. Don't use any of these standard deviation or standard error. Go to more error bars. So a new window opens and you go to custom here and specify the value. And now it asks you what the error bar should be. And what you can do is really, you just highlight with the left mouse button, you highlight all your margin of errors. And that is for the positive value and also for the negative value. Now click OK. And what you see now is really nice error bars. Yeah, that's a little bit too close for my liking. So here you have now your nice error bars. And what you notice is that the error bars actually reflect the margin of error. So we can be fairly sure, let me write that down. We can be fairly sure that our true mean for the data is in between here. Somewhere in here. Now for C, we have a huge margin of error. But in a way, this is not surprising, because if we look at it, we have one data point that really sticks out. That's this guy here. And that really makes our data, our margin of error quite large. So this is a nice way of representing your data. One thing that you very often see representing your data is where people draw bar charts, where it basically looks like that. And that is generally not terribly good practice. So if you try to publish in a high quality journal, they would not allow you that, because a bar chart doesn't mean anything. It would indicate that your data go from here, from the bottom, from 0 to here, but they don't. They are just an individual point here. So always go for this kind of representation. Okay, does that make sense? Now we are not yet done. What we also want to do is we want to say, right, now is there a difference between the untreated cells and the drug-treated cells? So let me write this down. That is why we do the experiment. Is there a difference? Is there a difference between untreated and drug-treated cells? Or in other words, does the treatment with one of the drugs lead to an effect? And we can write our null hypothesis, H null. This is, there is no difference. There is no difference. And all the differences all differences are due to sample error, to sampling error. It's just by chance. It's just sampling error. Now, how can we do that? For that, we use simply what is called the t-test, and you have done that in your first year, BI 308. So how is this done in Excel? So we compare, for example, the untreated cells with the drug A treated cells. And what we do is we just simply say equals T, and usually it comes up with a t-test. So you just double click on that. Oops, that was a little bit too hasty. So it asks us for our first samples. That's the array 1. So that's this one here, G5 to G8, comma. Then it asks us for the second array. That is this one here. Okay? And then it asks us for the tails. How many tails do we want? And tails simply means we say either there is no difference, there is a difference. So there is a difference between the samples. But we don't specify which direction, whether one is bigger than the other or the other one is bigger than the first one. That would be a two-tailed test. And I always would go for a two-tailed test. So in this case, we just simply put the number 2 in. And the last one that this is asking us is, what kind of test do you want? And if we compare a situation before and after, this is a paired test, and that has code number 1. If we compare two independent samples, where the sample variance or also the standard deviation is the same, this gets code 2. But we know that our sample standard deviations are different, which we see here. So it would be 2 independent standard deviations different. So that gets code 3. So all we need to do now is put this 3 here, close the bracket. Press enter. And what we get now here is our p-value. This is our p-value. Our p-value is 0.016. Let me write this again, p-value. This is our p-value here, 0.06. Now, what does that mean? If you remember, let me get rid of this. If you remember, if P is low, and this means low means smaller than our alpha value. And we said our alpha is 0.05. So if P is smaller than 0.05, if P is low, H naught must go. Okay? So low P means we reject our null hypothesis and we say the samples are different from each other. So 0.016 is definitely smaller than 0.05, and therefore we can say untreated cells are different from the cells treated with treated with drug A. So obviously, and this difference is not due to just simply sampling error or by chance, there is a real effect there. So very clearly we can say drug A has an effect. Drug A has an effect. Of course we can do that for other combinations. So for example we can ask what happens if we look at untreated with drug B, so equals t-test again we are here, and we compare that with sample B like that. We again go for a two-tailed test and the code is 3 for different variants. And again we get a p-value of 0.016. So again B has an effect. We can also compare A with B. Is A similar to B? So we can do that equals T distribution t-test. This is now we compare A with B, comma, two-tailed, not identical variants. And what we get here is we get a p-value of 0.98. So this tells us the question would be, is the difference between A and B drug-treated samples, drug cells, different or just chance? And since our P, if P is, that's not PIS, it is P is high, so P higher than alpha, 0.05. If P is high, then H naught can stay. And you have to say that with an Australian accent. So in this case, this means P is higher than alpha, 0.05, and therefore we can say the difference between A and B is just simply by chance. So in a way, A and B have a similar effect, on the cell growth. So hopefully with these tools, people are now able to analyze their data. And if you've got something like untreated cells, treated cells, you should be able to present the data in a nice graph. Obviously, you would have to have an axis label. You would have nice text boxes here. And you can also compare whether your treatment has an effect. So if you compare it, the untreated cells with the treated cells, you can calculate a p-value and you get a good information about whether your drugs are doing something, whether they are efficient or not. So I hope this makes sense. Thank you very much for watching, and enjoy your project. So thanks a lot, and if you've got any questions, drop me a line or send me a comment on Facebook, or just get in touch with me. Okay, take care, bye-bye, and enjoy your project.